Tonight, let us move slowly through one of the central mathematical questions of modern artificial intelligence. Our theme is how large language models learn, how they improve as they grow, and how they manage, at least in many cases, to perform well on examples they were never shown directly. We will not use formulas. We will not rely on symbolic notation. Instead, we will use careful language, patient repetition, and intuitive description. The subject is modern, but the deepest questions are very old. How does a system learn from experience? How does it discover pattern from limited evidence? How does success on past observations become competence on future observations? And how does complexity help rather than destroy understanding? Let us begin gently. A large language model is, at its heart, a system trained to predict pieces of language from surrounding context. It is shown vast amounts of text. It sees sequences of words, fragments of sentences, paragraphs, documents, and many other patterns. During training, it repeatedly tries to guess what should come next, or what token best fits the context it has been given. Its internal parameters are adjusted a little at a time so that its predictions improve. That is the operational story. But mathematically, something deeper is happening. A very large, very flexible function is being fitted to data. The data are not random in the everyday sense. They come from human language, from writing, from dialogue, from books, articles, code, and many other sources. All of this language reflects structure in thought, structure in society, structure in grammar, structure in fact, and also structure in error. A language model does not see the world directly. It sees traces of the world through text. It is worth repeating this. The model learns from text, not from reality itself. It learns from samples, not from the full underlying process that generated them. Already, this introduces one of the most important mathematical themes of the entire discussion, the gap between observed data and the broader distribution from which those data are drawn. We will come back to that many times. Before discussing generalization, robustness, and theory, let us pause and reflect on one of the most striking discoveries in modern language modeling, scaling laws. Scaling laws are empirical mathematical regularities. That phrase matters. They are not just casual engineering observations. They are not just vague impressions that bigger models seem better. A scaling law says that when we change quantities such as model size, amount of data, or total computation, performance changes in a systematic and surprisingly predictable way. In other words, progress is not chaotic. It is not only trial and error. There are smooth quantitative trends. A useful way to think about this is to imagine plotting model quality against model size. If the world were messy in an uncontrolled way, one might expect irregular jumps, long flat stretches, strange reversals, and no clear relation at all. But what researchers often observed instead was a kind of orderly improvement. As models became larger, and as training data and computation also increased in coordinated ways, errors often decreased according to stable patterns. This changed the field. Why did it change the field? Because it suggested that modern progress in language models is deeply tied to scaling behavior. Once people saw that performance could improve predictably with size and data and compute, training larger models stopped looking like blind optimism and started looking like an informed mathematical strategy. Let us say that again in a calmer way. Scaling laws tell us that size matters, but not in a vague way. They tell us that there are quantitative relationships between the amount of capacity in a model, the amount of information in the data, the computational effort spent during training, and the level of error we should expect. This is important because it reframes the entire enterprise. Instead of asking only whether a given architecture works, one can ask how performance should evolve as resources increase. One can ask what bottleneck is most limiting at a given moment. Is the model too small for the data? Is the data too limited for the model? Is there too little computation to properly benefit from both? These are mathematical questions of trade-off. The idea of a trade-off is central. A model can be very large, but if it has not seen enough diverse data, it may not use its capacity effectively. A model can have access to enormous data, but if it is too small, it may not be able to represent the relevant structure. A model can have both size and data, but insufficient optimization effort may prevent it from reaching a strong solution. So scaling is not only about making one quantity larger. It is about balancing several quantities whose interaction determines performance. This brings us to learning from data more broadly. A language model is trained on a finite sample. No matter how large the corpus is, it remains a sample. It is not the totality of language. It is not the totality of human knowledge. It is not even the totality of the internet, books, or code. It is a finite collection of observed examples. Mathematically, we imagine that these examples come from a broader distribution. The word distribution here should be understood very carefully. It does not simply mean a histogram or a bag of frequencies. It refers to the underlying probabilistic process that governs what kinds of examples appear, how often they appear, and how they are structured. When the model trains, it does not have access to this full underlying distribution. It only has access to the sample. This is where empirical risk minimization enters the story. Empirical risk minimization means, in plain language, that the model is adjusted to perform well on the data it actually sees. It minimizes training error, or more precisely, some training objective defined on the observed sample. The word empirical means based on observation. The word risk refers to expected error or loss. So empirical risk minimization means minimizing observed average error on the training sample. That sounds natural, and it is. If we want a system to learn, we give it examples and reward it for doing well on those examples. Over time, it improves on the sample in front of it. But a deep difficulty appears immediately. Success on the training sample is not the same as success on the true underlying distribution. A model can fit what it has seen but still fail on what it has not seen. This distinction is absolutely fundamental. Let us pause and restate it. Training concerns the observed sample. Deployment concerns the broader world. A model is fitted to one thing and then used on another. Those two things may be similar, but they are never identical. Generalization is the name we give to success across that gap. So when a language model performs well on new prompts, new documents, new tasks, or new settings, we say it generalizes. It is not merely repeating memorized training fragments, though memorization can certainly occur in some cases. It is doing something broader. It has extracted patterns that remain useful beyond the exact examples it saw. Now this raises one of the most fascinating puzzles in modern machine learning. Classical intuition often says that if a model is extremely flexible, with very many parameters, it should be prone to overfitting. It should be able to memorize a sample too closely. It should fit noise and become brittle. And yet many overparameterized models, including large language models, often generalize much better than naive classical intuition would suggest. Why? This is one of the major mathematical questions of the field. High-dimensional learning behaves differently from low-dimensional intuition. In small problems, one can often picture a simple curve fitted through a small cloud of points. Too much flexibility seems obviously dangerous. But in very high dimensions, with structured data, specific architectures, and particular optimization procedures, behavior changes. Geometry changes. Probability changes. The notion of complexity itself becomes more subtle. It is worth repeating that this is an active research area. There is no single final theorem that explains everything. There is no universal one-line answer to why large language models generalize as well as they often do. There are theories, partial explanations, important insights, and many unresolved questions. That uncertainty is part of the mathematics, not a failure of it. Let us now slow down and explore what generalization really means. A model generalizes if it performs well on examples that were not in the training set but are still drawn from a related distribution. The phrase related distribution matters. Generalization is not magic. It does not mean success on arbitrary nonsense. It means that the patterns learned from the sample continue to hold, at least approximately, in the wider population of relevant examples. Suppose a model has learned many regularities of syntax, semantics, discourse, style, and factual association from a broad corpus. Then when it encounters a new sentence, it can often respond sensibly because the new sentence shares underlying structure with many earlier examples, even if the exact wording is novel. So generalization is not memorization of exact strings. It is successful adaptation of learned statistical structure to new instances. But generalization in large models is not only about the model size. It is also about the data distribution. If the training sample is broad, diverse, and representative in the right ways, generalization tends to be better. If the sample is narrow, biased, or incomplete, then deployment can expose weaknesses. This leads naturally to distribution shift. Distribution shift occurs when the conditions at deployment differ from the conditions at training. In simple language, the model is tested in a world that is not statistically the same as the world it learned from. This mismatch can be mild or severe. A mild shift might involve a new writing style or a new topic that is still close to familiar material. A severe shift might involve a new language variety, unusual formatting, domain-specific jargon, adversarial prompts, unfamiliar reasoning patterns, or entirely new cultural contexts. The more deployment drifts away from training, the less confidently we should expect the model to behave. Again, it is worth repeating, models learn from finite samples drawn from broader distributions, and deployment occurs in reality, not in the training dataset. The gap between these is the central problem of generalization and robustness. Now let us turn to regularization, implicit bias, and stability. Regularization, in a broad sense, means introducing some form of control over complexity or behavior. In older and simpler models, regularization might mean explicitly penalizing large parameter values or discouraging overly complicated fits. The purpose is to prevent fitting from becoming too wild, too sensitive, or too dependent on accidental quirks of the training sample. But in large neural networks, something interesting happens. Even without an explicit complexity penalty in the simplest traditional sense, the training procedure itself can impose structure. This is where the idea of implicit bias appears. Implicit bias means that the optimization method, the architecture, the initialization, and the training dynamics together tend to prefer some solutions over others. Even if many parameter settings fit the training data equally well, the actual learning process may consistently find a certain kind of solution. That preferred kind of solution may have better generalization properties. This is a profound point. The loss function alone does not determine the outcome. The route by which the model is trained matters. Two solutions may both perform well on the sample, but one may be smoother, more stable, more compressible, or better aligned with the geometry of the data. Optimization may naturally drift towards such solutions. So successful learning depends on more than fitting the loss. Let us say it once more, because it is easy to forget. Training does not simply search the entire space and choose any point with low error. It follows a path through an enormous parameter landscape. That path has preferences. Those preferences create implicit bias. Stability is closely related. A stable learning procedure is one whose output does not change too drastically when the input data are perturbed slightly. If removing or changing a small portion of training data causes the learned model to behave wildly differently, we call that unstable. If the learned behavior remains broadly similar, we call it more stable. Stability matters because unstable systems are harder to trust, harder to analyze, and often worse at generalization. If a model's learned behavior depends too strongly on accidental fluctuations in the training sample, then it has probably not captured robust underlying structure. So stability, regularization, and implicit bias all point toward the same broad idea: good learning is not merely low training error. Good learning involves control, robustness, and preference for structured solutions. Now let us move toward representations, especially embeddings. When a language model processes words or tokens, it does not treat them as isolated labels. Instead, it maps them into high-dimensional vector representations, often called embeddings. We are avoiding symbols tonight, but the intuition is simple. Each word or token is associated with a location in a learned abstract space. Similar words tend to occupy related regions. Differences in meaning, usage, or context can correspond to directions or separations within that space. Why is this useful? Because geometry can encode relationships. If two terms appear in similar contexts across many documents, the model often places them near one another. If certain semantic distinctions recur consistently, the embedding space may organize itself around those distinctions. Clusters can appear. Directions can become meaningful. Regular patterns can arise. This is one of the most beautiful ideas in representation learning. Meaning can become spatial structure. Let us pause and reflect on that. The model does not possess meaning in a human introspective sense, but it learns representations in which semantic relations often correspond to geometric regularities. Similarity becomes closeness. Contrast becomes separation. Shared structure becomes alignment along certain directions. Of course, this geometric picture is imperfect. Real embedding spaces are complex. They are not simple maps where every concept sits in one clean location. Meanings depend on context. Polysemy, ambiguity, and compositionality complicate everything. Still, the spatial metaphor is mathematically powerful because it captures how statistical regularity in language can induce structured representation. This geometric viewpoint helps explain transfer learning as well. For training on a large corpus builds general-purpose representation. These representations encode many regularities of language, and world knowledge is reflected in text. Later, fine-tuning or adaptation can specialize the model for narrow domains or tasks. The important point is that the system does not start from scratch. It begins with a rich internal geometry that already contains useful structure. Fine-tuning is therefore not merely adding information. It is reshaping an existing representation system. Transfer learning means that knowledge acquired in one setting becomes useful in another. A model trained broadly on general language can later perform well on specific domains because its internal features are not entirely task-specific. They capture patterns that transfer. This transfer is one reason pre-training is so powerful. It creates general representations first, and specialization later becomes easier. But the success of transfer also depends on similarity between domains. If the fine-tuning domain is related to pre-training data, adaptation may be smooth. If it is very different, the model may struggle. Again, distribution shift reappears. Now let us discuss singular values, rank, and compression in an intuitive way. Large language models contain enormous matrices of parameters. At first glance, these matrices may seem fairly dense and wildly complicated. One might imagine that every parameter is independently essential. But in practice, many learned parameter matrices exhibit compressible structure. This means that although the system is large, its effective organization may be governed by fewer dominant patterns. The language of rank and singular values belongs to linear algebra, but the intuition can be stated gently. Imagine a huge table of numbers representing some learned transformation. Although the table is large, it may be that much of its behavior can be approximated using a smaller collection of dominant modes. Some directions matter a great deal. Others contribute little. Some combinations carry most of the structure. Others are minor refinements. When this happens, we say the matrix has low-rank tendencies or spectral concentration. In simpler words, the information is more organized and compressible than raw size alone would suggest. Why is this important? First, for efficiency. If a learned transformation can be approximated while using fewer dominant components, then storage and computation may be reduced. Second, for understanding. Compression often reveals that the model is not using all degrees of freedom equally. It is discovering structured internal representations rather than arbitrary chaos. Third, for theory. Compressibility hints that even in giant models, the learned solution may lie on only a more orderly subset of the full parameter space. This is worth repeating. A very large model may still learn something relatively organized. Huge size does not imply complete disorder. Large systems can develop lower dimensional structure inside high dimensional ambient spaces. That tension between enormous raw dimension and smaller effective dimension is one of the recurring themes of the mathematics of large language models. Now let us turn to the loss landscape and optimization geometry. Training a language model means adjusting parameters to reduce some objective measuring predictive error on training data. If we imagine every possible parameter setting as a point in an enormous space, then the loss assigns a height to each point. High loss means poor performance. Low loss means better performance. Training becomes a descent through this landscape. The phrase landscape is useful, even though the true object lies in extremely high dimensions far beyond ordinary visualization. In low-dimensional metaphors, one thinks of hills, valleys, basins, ridges, and plateaus. In high dimensions, these are only analogies, but they remain informative. Some regions correspond to poor solutions. Some are broad and forgiving. Some are sharp and brittle. Some contain many different parameter settings with similar performance. The geometry of this landscape matters enormously. For example, two minima can have similar training error but different generalization behavior. A flatter region may correspond to a solution that is less sensitive to small perturbations in parameters. A sharper region may fit the sample tightly but behave less stably. Researchers debate exactly how to formalize these ideas, but the broad intuition remains influential. Not all minima are equally good, even if their training loss is similar. Optimization success therefore depends on geometry as much as on algorithms. It is not enough to say that gradient-based methods move downhill. We must ask what kind of regions they tend to find, how curvature affects movement, how noise and optimization influences the path, and how the geometry of data interacts with the geometry of parameters. Neural training is, in this sense, a geometric process in parameter space. This connects directly to symmetry and redundancy. In many neural networks, different parameter settings can represent essentially the same function or very similar functions. For instance, units may sometimes be permuted or rescaled in ways that leave the overall behavior largely unchanged. More broadly, some directions in parameter space may matter a great deal for output behavior, while others matter very little. This means the parameterization is redundant. Redundancy complicates theory because the raw number of parameters does not directly measure functional complexity. Two seemingly different points in parameter space may actually encode nearly the same input-output behavior. So when we speak of model size or complexity, we must be careful. Counting parameters is informative, but it is not the whole story. Symmetry also means that optimization landscapes may contain entire families of equivalent or near-equivalent solutions. Instead of isolated best points, there may be wide connected regions of similarly good behavior. This changes our intuition about what optimization is doing. It is not necessarily finding a single needle in a haystack. It may be entering a large basin of functionally similar models. Again, let us pause and reflect. Different parameter settings can represent similar functions. Not every parameter direction changes behavior meaningfully. This is one reason large models can be hard to analyze. The parameter space is huge, but much of that hugeness reflects redundancy, symmetry, and effective compression rather than independent, meaningful degrees of freedom. Now we return to fine-tuning and domain adaptation in more detail. A pre-trained language model has already learned broad structure from a large corpus. Fine-tuning adjusts this model for a narrower task or domain. Perhaps legal language. Perhaps medical writing. Perhaps coding assistance. Perhaps a particular conversational style. Mathematically, the key idea is that pre-training constructs a strong prior representation. Fine-tuning then performs a localized adaptation. Rather than learning language from zero, the model modifies existing internal organization to better match a narrow distribution. This is often more efficient and more effective than task-specific learning from scratch. Transfer learning works because many structures in language are reusable. Syntax transfers. Many semantic relations transfer. Broad world regularities transfer. Even some reasoning patterns may transfer in partial form. Pre-training creates a foundation and fine-tuning reshapes it. But adaptation has risks. A narrow fine-tuning process may over-specialize the model. It may distort capabilities outside the target domain. It may introduce biases associated with the new data. Or it may fail if the new domain differs too much from what pre-training prepared the model for. So fine-tuning is not merely about improvement. It is about navigating a new distribution while preserving useful old structure. This leads us back again to distribution shift and out-of-distribution behavior. An out-of-distribution input is one that differs significantly from the inputs the model was effectively trained on. This does not always mean bizarre nonsense. It can be a subtle mismatch. A new dialect. A rare domain. A prompt style unlike those seen before. A combination of concepts that occurs extremely rarely in training. A question requiring a kind of compositional generalization that the model has not robustly learned. Models can fail systematically in such settings. Not randomly, but systematically. This is important. Failure is often structured. Because models are sensitive to the geometry of data, changes that seem small to humans may move an input into a sparse or poorly represented region of the learned space. The model then extrapolates badly. That is why robustness matters so much. Robustness asks whether performance remains acceptable under perturbation, uncertainty, or shift. A robust model is not merely good on average familiar examples. It remains competent when inputs are noisier, rare, slightly altered, or somewhat misaligned with training conditions. Probability theory enters here because average case performance and worst case performance are very different things. A model may perform extremely well on the typical sample drawn from the same distribution as training data. But deployment often exposes tails, rare cases, edge cases, and adversarial manipulations. The average can hide the dangerous corners. This is where adversarial perspectives become useful. An adversarial example is an input modified in a carefully chosen way that causes the model to make a poor prediction, often despite the change seeming small or irrelevant from a human point of view. In language, adversarial structure can involve phrasing tricks, misleading context, unusual token patterns, prompt injections, or other constructions that exploit weaknesses in learner decision boundaries. The central lesson is that small input changes can produce large output changes if those changes push the example across sensitive regions of the model's internal geometry. Let us say this again slowly. A system can be accurate on average and fragile in carefully chosen cases. Worst-case analysis is therefore different from average-case success. Safety and reliability require attention not only to what usually happens, but also to what can happen under structured perturbation. This perspective is especially important for deployment in high-stakes settings. If we want mathematical guarantees, we must think beyond average training and average testing. We must ask about rare failures, instability, uncertainty, and the limits of what probability-based sequence prediction can ensure. And this brings us to theoretical limits. Large language models are probability-based sequence models. They learn to assign high likelihood to plausible continuations and lower likelihood to implausible ones, based on statistical regularities in text. This is a powerful framework. It allows broad linguistic competence, flexible generation, and impressive adaptation. But probability-based next token prediction does not automatically imply deep reasoning, grounding in external reality or truth. That distinction matters enormously. A model can produce text that sounds coherent without being correct. It can imitate explanation without possessing verified understanding. It can follow patterns associated with reasoning without guaranteeing valid reasoning in the strict logical sense. This is not to deny capability. It is to clarify its nature. Prediction is not the same as truth. Fluency is not the same as grounding. Statistical success is not the same as formal guarantee. Let us pause and reflect on the word grounding. Grounding refers to connection between internal representations and the external world in a way that supports stable reference and reliable truth tracking. Language models trained only on text have indirect access to the world through descriptions, reports, arguments, and narratives. Those are rich and useful, but they are mediated. The model learns correlations in text, not direct physical interaction with reality. Similarly, reasoning has multiple senses. There is practical competence at producing useful chains of explanation. There is pattern-based imitation of reasoning forms. There is genuine rule-governed deduction in narrow formal systems. There is deliberative problem-solving with verification. These are related but not identical. Strong empirical behavior in one sense does not automatically yield guarantees in another. This is why the theoretical limits of language models matter. We want to know not only what they often do, but what can be guaranteed, what cannot be guaranteed, and why. There are computational limits and statistical limits. Computational limits concern what can be achieved given finite time, memory, and optimization resources. Even if a target function exists in principle, finding it may be too expensive. A model may have enough expressive power but not enough computation to realize it effectively. Statistical limits concern what can be learned from finite data. If the training sample does not contain enough information about a phenomenon, no clever optimization can fully recover it. Data impose limits. Some distinctions are unidentifiable from the available sample. Some error events cannot be modeled reliably if they occur too infrequently. So even very large models remain bounded by data, computation, and objective design. Now let us gather some of the threads we have developed and revisit them in a more unified way. First, scaling laws. Performance in large language models often follows surprisingly regular quantitative patterns as model size, data size, and compute increase together. This means progress is not merely accidental engineering. It reflects empirical mathematical regularities. Second, empirical risk minimization. Models are trained to reduce error on a finite observed sample. This is natural, but it creates the fundamental gap between training success and deployment success. Third, generalization. A model succeeds not because it only memorizes exact examples, but because it captures statistical structure that extends beyond the sample. Yet why this works so well in overparameterized settings remains an active area of mathematical research. Fourth, regularization, implicit bias, and stability. Good learning is not only low loss. It also depends on what kinds of solutions optimization prefers and how sensitive those solutions are to perturbation. Fifth, embedding geometry. Learned representation spaces often exhibit clusters, directions, and semantic organization. Meaning, in an important mathematical sense, becomes spatial structure. Sixth, compression and spectral structure. Very large parameter systems may still contain dominant low-dimensional organization, making them more compressible and interpretable than raw size alone would suggest. Seventh, loss landscapes and redundancy. Training occurs in enormous parameter spaces with complex geometry, many equivalent or similar solutions, and substantial symmetry. Optimization is therefore a geometric and dynamical process, not just a static minimization problem. 8. Transfer learning and domain adaptation. Pre-training creates reusable representations that can later be specialized, but success depends on how closely new domains align with what the model has already learned. 9th. Distribution shift and robustness. Real deployment differs from training. Models can fail on unfamiliar, rare, or adversarial inputs, and average success does not guarantee safety in worst-case settings. 10th. Theoretical limits. Statistical prediction over language is powerful, but it does not automatically guarantee reasoning, grounding, truth, or immunity to failure. Formal understanding still trails behind empirical success. It is worth repeating that these ideas are not isolated. They connect. Scaling affects representation quality. Representation quality affects transfer. Transfer interacts with distribution shift. Distribution shift exposes the limits of generalization. Generalization depends on implicit bias, stability, and optimization geometry. Optimization geometry is shaped by symmetry, redundancy, and high-dimensional structure. Compression hints that large models may learn more organized internal structure than parametric counter-learn suggests. And all of this unfolds under finite data and finite computation. This is the mathematical picture. Not a single theorem, but a network of interlocking themes. Let us spend a little more time on the high-dimensional aspect, because it is easy to underestimate how much it changes intuition. In very high dimensions, distances, concentrations, and geometric relations behave differently from the low-dimensional worlds we can easily visualize. Data often linear structured manifolds or low-dimensional subsets. Random directions may matter little, while a few meaningful directions matter a great deal. Optimization can exploit concentration effects. Large representation spaces can separate patterns that would be entangled in smaller spaces. So when we ask why a huge model can generalize, part of the answer may be that the data themselves possess hidden structure that becomes easier to represent once the ambient dimension is sufficiently rich. Another part may be that optimization finds structured solutions that align with this hidden organization. Another part may be that language itself contains deep redundancy, regularity, and compositional patterns that large models can exploit. No single sentence captures it all. It is worth repeating that modern language models are not miraculous exceptions to mathematics. They are invitations to expand mathematics. They force us to refine our notions of complexity, effective dimension, optimization bias, and statistical structure in large-scale learning. And that is one reason the subject is so compelling. Now let us soften the pace and think about one more central distinction: empirical success versus formal understanding. Empirical success means that a model performs well in experiments, benchmarks, tasks, or practical use. Formal understanding means that we can explain this success with rigorous theory, precise assumptions, and reliable guarantees. In large language models, empirical success has moved faster than formal theory. We can observe remarkable capabilities, measure strong benchmark performance, and identify scaling regularities. But our theorems often explain only pieces of the story, or simplified settings, or idealized models. That is not unusual in science. Practice often outruns theory for a while. Then theory catches up gradually, often by inventing new concepts. We should not mistake the current gap for permanent mystery, but neither should we pretend it has already been closed. So if you feel that some of these topics remain unresolved, that feeling is correct. It is part of the honest mathematical situation. Let us pause and reflect. A language model learns from a finite sample. It minimizes observed error. It develops internal geometric representation. It benefits from scale. It generalizes beyond exact examples, though imperfectly. It inherits implicit biases from optimization. It may be compressible despite enormous size. It operates within a complicated loss landscape shaped by redundancy and symmetry. It can transfer knowledge to new tasks. It can also fail under distribution shift or adversarial perturbation. And its impressive behavior still exceeds our complete formal understanding. This is a lot to hold in mind, so let us say it in an even quieter and more unified way. Large language models are learned statistical systems living in very high-dimensional spaces. They are trained on finite data, optimized with vast computation, and shaped by both architecture and dynamics. Their success depends not only on raw size, but on the balance between size, data, and optimization. Their internal representations often acquire geometric regularity. Their learned parameters often exhibit hidden structure and redundancy. Their outputs can be powerful and useful, but also fragile and limited. Their behavior is partly understood, partly mysterious, and deeply mathematical throughout. As we move toward the end, let us return to the first theme, learning from samples. This may be the quiet center of everything. Any learner sees only part of the world. From that part, it must infer patterns that will remain useful later. Too much flexibility invites memorization. Too little flexibility prevents adaptation. Too little data leads uncertainty unresolved. Too much mismatch between training and deployment breaks trust. Good learning lies in the tension between all of these. Large language models occupy this tension at extraordinary scale. That is why they are scientifically interesting. They are not only tools. They are experiments in high-dimensional statistical learning, representation geometry, optimization dynamics, and probabilistic generalization. And because they are so large, they reveal regularities that smaller systems could not make as visible. Scaling laws become measurable. Representation geometry becomes rich. Transfer becomes broad. Failure modes also become more consequential. Both the power and the limitations grow clearer. Now let us conclude slowly. We began with the question of how large language models learn, scale, and generalize. We saw that scaling laws describe smooth empirical relations between performance and key resources such as model size, data size, and computation. These laws suggest that modern progress is tightly connected to quantitative regularity. We saw that models trained by minimizing observed error on finite samples, and that this immediately creates the central challenge of generalization, doing well beyond the training data. We considered the puzzle of overparameterization, where extremely flexible models can still generalize surprisingly well, especially in high dimensions where classical intuition is incomplete. We discussed regularization, implicit bias, and stability, which remind us that learning depends not only on what is fitted, but on how it is fitted and how sensitive the result is to perturbation. We moved through the geometry of embedding spaces, where semantic similarity becomes spatial organization, and where learned meaning often appears as clusters, directions, and structure. We reflected on compression, rank, and spectral concentration, which suggests that large models may contain more order than their raw size first suggests. We explored loss landscapes, flatness, sharpness, basins, and redundancy, and we saw that optimization is as much a geometric journey as it is an algorithmic routine. We considered fine-tuning and transfer learning, where pre-training builds general representations that later adaptation can specialize. We return many times to distribution shift, out-of-distribution behavior, adversarial fragility, and the difference between average case success and worst case reliability. And finally, we consider the theoretical limits of language models, emphasizing that strong prediction does not automatically imply truth, grounding, or guaranteed reasoning. So the unifying picture is this. A large language model is a vast statistical learner trained on finite text data. Its improvement with scale follows striking empirical regularities. Its success depends on geometry, optimization, stability, and representation. Its generalization is real, but conditional. Its failures are informative. Its internal structure is often more organized than it first appears. And its capabilities, however impressive, must still be understood within the limits imposed by data, computation, probability, and theory. It is worth repeating one last time that this remains a living mathematical field. The questions are open. The theories are developing. The phenomena are rich. And the gap between practical achievement and formal explanation is itself one of the most interesting objects of study. Let us then there, with that quiet idea. Not that the mystery has vanished. Not that the system is fully understood. But that learning, scaling, and generalization in large language models form a coherent mathematical landscape, one that rewards patience, abstraction, and careful thought. And if you drift away from the details, perhaps the central memory to keep is simple. These models learn from limited data. They improve with scale in regular ways. They organize language into geometry. They generalize beyond what they saw, but not without limits. And understanding why is one of the great mathematical questions of our time.